Ja, herzlich willkommen. Ich grüße Sie, auch die neu hinzugekommenen, ganz herzlich zur 13. Deutschen Klimatagung. Der Plenarvortrag heute ist auch öffentlich als Webinarform zu hören und zu sehen. Das ist meines Wissens das erste Mal, dass wir das auf der DKT so machen. Ich bin ja gespannt, ob sich das etablieren wird. Und unser Gast heute ist Professor Dr. Johann Rockström. Und er wird seinen Vortrag auf Englisch halten und deswegen wechsle ich jetzt auch ins Englische. I'm very happy to welcome Johann Rockström for this plenary talk today. Johann is director of the Potsdam Institute for Climate Impact Research, one of the institutes here hosted at the Till Grafenberg, which are supporting this conference. He's also professor at the Institute of Earth and Environmental Sciences at the Potsdam University and professor in water systems and global sustainability at Stockholm University. Before becoming director of the Potsdam Institute of Climate Impact Research, Johann founded the Stockholm Resilience Center at Stockholm University. He received several prizes in the last years and is ranked as one of the most influential and most cited scientists in the world by Clarivate Analytics. Johann gained international recognition with the development of the Planetary Boundaries framework, and I'm happy that he agreed to give a plenary talk today on this topic. Taking the pulse out of our planet with safe and just planetary boundaries. Johann, the floor is yours. You can share your screen.
Thank you so much. And it's a pleasure and an honor to be with you at this Deutsche Klimatagung. And yes, I'll be sharing my screen. And what I want to do is to give you a scientific update on where we are with regards to the state of our planet, but also to give you the lines of science that brought us to the planetary boundary framework and what the science is pointing at when it comes to the future as well. So it will be a piece of 3 parts. One of the diagnostic of what we are seeing today, the evidence behind the planetary boundaries, and then where we are heading scientifically as we continue. And the startup of any talk, I would argue today, with regards to the challenges we're facing as humanity, as people on planet Earth, must be the scientific, and I would argue unequivocal, evidence that we are not only in the Anthropocene, the new geological epoch that is suggested by science, where we, anthros, Greek for humans, are the dominating geological force of change on planet Earth. We're also deep into the Anthropocene. The scale and the speed and the interconnectivity of the globalized world in the 21st century has come to a point where we are, one, starting to hit having evidence of hitting the ceiling of hardwired processes that regulates the function, the stability, and the resilience of the whole Earth system, and that we are at a point when we can no longer exclude causing irreversible changes that can trigger a drift away from the state of the Earth system that we depend on for human civilizations. This has been summarized in many different pieces of evidence. One of them is the State of the Climate report that Bill Ripple and others, I was part of this work, put out last year, just looking at the annual update of what happened 2023, with the off-the-charts observations we're starting to experience in terms of Antarctic sea ice extent, surface temperatures in the ocean, accelerated melting of the West Antarctic ice sheet, not only having massive, step-by-step, year-by-year increase, but also a sudden off-the-chart deviation during this human amplified super El Nino year of 2023. This has forced us, not only of what we're observing 2023, but also over the last few years, to be, as a scientific community, forced to pose the following question. Are we at risk? Are we approaching a state shift in the feedback dynamics of the Earth system? Is Earth losing resilience? Are we heading towards a point where we cannot exclude an irreversible trajectory away from the state that we have been privileged to have over the last 10,000 years since we left the last ice age? Now, added to the challenge is that more and more scholars are feeling forced to also look at the risk of approaching a polycrisis. So it's not only that the Earth system is showing signs of losing its function and stability, but we're also having multiple global crises occurring simultaneously, like the war in Ukraine and Gaza, economic recession and inflation, food insecurity and undermining of democratic structures around the world, causing social instabilities. And when these interact and reinforce each other, are we approaching a point of a polycrisis? I just want to have that as a backdrop in this analysis, because I feel that these uncertain but still very, very well-grounded, worrying indicators are fundamentally providing even more support for why we now need to provide a safe operating space for humanity on planet Earth, and why we need to measure the entire planet, and why we need to be concerned and actually start seriously considering how to be stewards of the entire system. Because we are deep into the climate crisis, and we all know the data. 2023, with a 1.48 degrees Celsius of global mean surface temperature rise. Sure, it's an El Nino, but it's a human amplified El Nino. To quote NASA, the ocean has fever, releasing unprecedented levels of heat from the western part of the Pacific, just west of Peru. We have the off the charts graph. I find this graph to be potentially the most worrying graph of them all today, with the blue lines showing the annual, quite linear, gradual increase in surface ocean temperature, rising within the order of 1 point soon 5 degrees Celsius, basically following the temperature rise in the atmosphere. Why? Because 90% of the heat from fossil fuel burning is in the ocean. Then you suddenly have this off the chart observation in yellow from 2023, which in itself was a shocking more than one standard deviation jump suddenly, which we cannot explain in our climate models. And then you have the red line here showing how 2024 just continues to go even further off the charts. The honest conclusion from this graph is we do not know what's happening, but something odd is occurring. There's some form of biophysical dynamic in the ocean that we cannot fully explain so far. It has impacts. We see the rate change in many of the big biophysical systems on Earth. Here's just one of those that is most clear from the late 1990s, how the Greenland ice sheet loses much more much more rapid rate of mass loss. So we see increasing signs of biophysical loss of resilience in the big tipping element systems that keep and are dominated by negative feedbacks, namely meaning dampening feedbacks, holding the Earth system stable. The Arctic is one of the ground zeros on planet Earth because it's warming 3 times faster than the planet on average. And many of the Earth system dynamics in their stability are, as we're increasingly seeing in the scientific record, originating from interconnections with what's happening in the Arctic zone. So what does the IPCC say about this? Well, in the 6th assessment of the IPCC, there is today an unequivocal agreement that we're in the midst of the climate crisis. Climate change is threatening human well-being today. We know that the invoice just 2023 was in the order of 300 billion US dollars just for the direct climate extremes, the storm, the floods, the droughts, the heat waves. But we're also seeing that the social cost of carbon today is exceeding 200 US dollars. Important conclusion in my mind is that even the IPCC now concludes at its highest level of summary for policymakers that we're threatening planetary health. We are at risk of destabilizing the planet. That's IPCC now also recognizes that to solve the climate crisis, it won't be enough to just phase out fossil fuels. We will need, as you see in the lower part here in C36 conclusion, that we also need to safeguard the carbon uptake capacity and the stability of the ecological functions in the biosphere. What does this mean? Well, it means that the planetary boundary framework has now come to a point scientifically where we can conclude that even if we only care about solving the climate crisis, we need a whole Earth system approach. We need to come back into the safe operating space on biodiversity, on land systems, on nitrogen, phosphorus, and fresh water, namely the biosphere systems. As you see, the IPCC even quantifies this, which is entirely in line with the planetary boundary quantification of its control variable. Up to 50% of nature on land needs to be kept intact to be able to hold the resilience of the system in the biosphere at a healthy level. Now, this is a very important number because, as you know, we've actually transformed in the order of 50% of the land area on planet Earth to agriculture, infrastructure, and cities. So this means that we've come to the end of the road of expanding agriculture in the world, which is exactly where we are on the planetary boundary science. Now, the evidence here has come a long way. The first planetary boundary science paper was published in 2009. And the reason why, or let's say what enabled us to do this, was not only the push from the evidence of the great acceleration in the Anthropocene, it was also that we had more and more evidence of the unique stability of the Holocene and the proof of how dependent we are on the Holocene, the interglacial equilibrium state of the Earth system since we left the last ice age some 12,000 years ago. But just to carry home this story in full, here is the whole Quaternary, the past 3 million years. This is the first attempt of using a mathematical physical model to reproduce the journey of planet Earth during the entire Quaternary with the Climate 2 model led by Matteo Willett and Andrzej Gonopolsky, colleagues of mine a bit further up the hill here in Telegrafenberg at the Potsdam Institute. What you see here is on the y-axis global mean surface temperature. The 0 point is the 14 degrees Celsius, the pre-industrial, before we start burning fossil fuels. The black line, you can drop that for the moment. That's the validation point up to 1 million years. It's ice core data. Further back, it's tree ring proxies and other proxies. The key is the green line here, the oscillation from the simulation runs. And the key message, which I find to be quite extraordinary, goes beyond just science. It's really a humble recognition that as far as we understand it, with a quite mainstream Earth system model, we show that at its warmest temperature, Earth never exceeded 2 degrees Celsius. That's the warmest point on planet Earth during the Quaternary. And the coldest point, deep ice age, is in the order of minus 5 degrees Celsius. And this is so significant because we know that if we go deeper into geological time, meaning further back than the Quaternary, we move away from the biophysical, the geophysical, and the biosphere configuration of the Earth system as we know the planet. So the planet, as we know it, has only existed over the past 3 million years. Now, I call this the corridor of life. It's a very narrow corridor, +2, the warmest temperature, -5, deep ice age, and it's within this narrow corridor, everything that we know and can call life has occurred. And we certainly depend on this corridor. But to make the point even stronger, when we leave the last ice age, some 18,000 years ago, starting to leave the most recent ice age, we enter this extraordinarily stable Holocene period. And as you see just from the graph, from this Osman et al. Summary, it's an even more stable state. It's a life corridor which is for 14 degrees Celsius ±0.5 during this entire period. And this is significant for us because we've been modern humans on planet Earth for 250,000 years. That's the latest assessment, at least, living through 2 ice ages, the Eemian as 1 interglacial. And then we leave the last ice age and we enter this extraordinarily stable Holocene state. And we transition from being a few million hunters and gatherers, living through very variable environmental conditions. And what do? We barely come into this very narrow, stable life corridor, and we go through the Neolithic Revolution. We become farmers, we domesticate animals and plants, and off we go in the civilizational journey as we know it. So the conclusion, which is a fundamental part of the evidence supporting the planetary boundary framework, is that the Holocene is the only state of the planet we know for certain can support the world as we know it. We've lived outside of the Holocene. Yes, we've lived in deep ice age. We've lived within the broader life corridor, but we have no evidence whatsoever that we can support with ethical and responsibility a world with 8, soon to be 10 billion people on planet Earth. So the Holocene becomes a reference point of a desired planet, the planet we depend on. So this is the drama. We now know the reference point of the planet we depend on, but we're pushing ourselves away from this point because we are in the Anthropocene. So this is the reality of where we are today. Now, it's even deeper than that, as I'm sure you're aware, because why has the planet stayed within this very narrow corridor of life? Well, it's because of the resilience in the biophysical and geophysical systems on planet Earth. It is not the solar radiative forcing and changes in the Milankovitch cycles that explains alone the transition between the ice ages and the interglacials. And the proof is, I would argue, in these two pieces of critical, key, important evidence. To the left-hand side is the global carbon budget released each year by the Global Carbon Project. On the x-axis, you have from 1850 until today. On the y-axis, gigaton of carbon. The classic hockey stick in gray, fossil fuel burning, in orange, deforestation. You recognize the graph. 10 gigatons of carbon released each year today. Is it all of this? Is it the area under this curve that has caused the warming, the 1.48 degrees Celsius, in the deep climate crisis we are faced with today? The answer is no. In dark green, we have the remarkable uptake of carbon in terrestrial intact nature on land. And in light green, you have the remarkable uptake in the ocean. So it's only the blue residual that has caused the warming so far. And even a kindergarten child will tell you, if he or she looks at this graph, isn't this interesting? The more we punch the planet, the more she's helping us. And that is exactly what is happening or has happened with a healthy planet, which has been showing this remarkable, persistent ability to buffer 50% every year of our climate debt in our fossil fuel burning by absorbing it through carbon dioxide fertilization on land and dissolving carbon predominantly in the ocean. But to the right, we have an even larger drama, as you know, with a 90% of heat uptake in the ocean. So the truth is that we have a planet, when configured in a healthy state, meaning being within the safe operating space of planetary boundaries, with this remarkable biogeophysical capacity to buffer and dampen stress coming, in this case, from human-induced warming. Now, this has to be connected to the third piece of science that builds up to the planetary boundary framework, namely the tipping point science. Because we also understand that the Earth system is a complex, self-regulating system configured in all its spheres with tipping element systems that have a characteristic of multiple stable states. So not only are they critical to be able to uphold this buffering capacity, this dampening capacity, the negative feedbacks that can keep us away from irreversible changes, they also have multiple stable states. You can push a system like the rainforest too far, and it will irreversibly shift into a savanna state. Or you have a permanent ice sheet that irreversibly starts melting and becoming a liquid surface. Now, what we're showing in the latest mapping of the climate tipping element systems, you see the graph here, is the David Armstrong McKay et al. Paper published in 2022. It's after the 6th assessment of the IPCC. These 16 tipping element systems are actually in the IPCC Working Group 1 report, but this is a more, let's say, scientifically rigorous criteria assessment. And the breakthrough here is the color scheme. It is that we've been able, for the first time, by mapping all the published research, so it's a synthesis of published research in the world, to for the first time get uncertainty ranges on temperature and median levels of the most likely temperature levels when these systems will cross their tipping points. So these 5 are the first ones on the line according to this assessment. The Greenland ice sheet, the West Antarctic ice sheet, 10 meters sea level rise together, all the tropical coral reef systems in the world, livelihoods to at least 300 million people, abrupt thawing of permafrost in the Arctic zone, and loss of the Barents Sea ice. Now, these are likely to cross their tipping points at 1.5 degrees Celsius. This, I would argue, well, not only is it a planetary boundary, because this is the methodology we've been using. Keep the planet as close as possible to Holocene interglacial conditions. Use tipping point science as one proof point to be able to methodologically define the boundary that you want to stay within to keep the system as close as possible to Holocene-like conditions, beyond which you risk triggering irreversible changes. And this is one piece of evidence, and that's what you see here on this screen. We also have, which is not in the IPCC, but is really at the frontier of this research, more evidence that these tipping element systems are interconnected in cascades. And this is a figure coming from, translated from a number of published papers, led not least from Nico Wunderling and colleagues at the Potsdam Institute. But it's appearing in the 10 New Insights in Climate Science. I mentioned that because every year we produce the 10 most important scientific advancements in climate science, which we summarize for the climate negotiators. We do this nowadays together with the World Climate Research Program, the Future Earth Network, and the Earth League. And this was one of the 10 New Insights in Climate Science in the 2021 10 NICs. And what this evidence shows is that when the Arctic, the ground zero that is warming 3 times faster than the planet on average, releases massive volumes of fresh water in the North Atlantic, it slows down the AMOC, which then has more evidence of pushing the monsoon system further south, which can explain why you get more rapid dieback because of droughts and fires of the Amazon rainforest, another tipping element. But it also means that you get more heavy, dense, warm, saline water residing in the Southern Ocean, which may be an explanation why you see that the West Antarctic ice sheet is melting faster than expected. This science thus proposes that you have an interconnection between the Arctic and Antarctica across cascades that interconnect tipping elements. And the AMOC, of course, we've been reading a lot about that the last few weeks with Westen et al. Paper from Utrecht, but also, of course, following the Ditlevsen and Ditlevsen paper just a few months back, all of them putting forward more and more warning signs that the AMOC is not only slowing down, which is well verified through the Argo buoy and the observations in the ocean, but also that we cannot exclude a shutdown of the AMOC. We know that the AMOC has been shutting down several times before. The last time was quite recently, actually, as far as we know, just when we left the last ice age, some 12, 15,000 years ago. As you know, it's an important system regulating weather systems, not only in the Northern Hemisphere, but actually temperature levels across the world, but also impacting on sea level rise and potentially also having massive impacts on the monsoon systems. The latest paper by Westen et al., in my view, is a very important contribution because it's the first time we really can verify the risk of a shutdown of the AMOC through a conventional big GCM model running with a 6-month period in Netherlands' biggest supercomputer, verifying that with a higher degree of Svendrup freshwater flowing, you get a shutdown, and a shutdown leads to massive impacts with a 20 degrees Celsius cooling in the Scandinavian part of the planet, but also major impacts across the world. That this paper does not say when this can happen, but it does verify or adds new further evidence that this is a risk we have to take very seriously. And we have more and more scientific evidence that this is something we need to take seriously. So there you have the entire set of sources of evidence that are used to build up the planetary boundary framework. We're in the Anthropocene, so we are putting the pressure at the planetary scale. The Holocene is the desired state of the planet, and tipping points are hardwired, they're real, and we have quite a lot of evidence behind them, helping us to quantify safe boundaries. The third scientific update of the planetary boundaries was published in late 2023. All the 9 boundaries have now been quantified. These are the 9, which I would argue we today have a very strong scientific basis that if we can be stewards of these 9, we have a good chance of keeping the Earth system in for us humans, livable, resilient, life support state, keeping the planet as close as possible to a Holocene-like state, but also having resilience to buffer stress. The boundaries include climate, ocean, stratospheric ozone layer. It includes air pollutants and novel entities, chemicals, but also 4 biosphere boundaries: biodiversity, land system configuration of big biomes, the freshwater cycle, the bloodstream of the Earth system, and also the biogeochemical flows of nutrients. 6 of the 9 boundaries are now assessed to be outside of the safe operating space. We're using, as you see here, the IPCC red embers normalized range of risk. The yellow zone here is the uncertainty range in the scientific assessment. So each boundary has a scientific uncertainty range, and the boundary is put as a normative decision on precaution at the lower end of the uncertainty range. So when you exit a boundary, doesn't mean that you fall over an escarpment and collapse. It means that you're entering a danger zone. And the deeper you go into the red, the higher is the risk of causing irreversible changes that can cause not necessarily, or very likely not, a complete collapse, but a drift where feedbacks start changing direction and you start losing this buffering capacity and instead move into more amplifying conditions. The Planetary Boundary Science has then been taken to the Earth Commission, an initiative launched 3 years ago of trying to create a global scientific assessment mechanism for all the science that attempts to quantify a safe but also a just space for humanity on Earth. So bringing in both the social sciences, but also kind of synthesizing beyond the planetary boundaries where we are on the biogeophysical systems that regulates the stability of the Earth system. The Earth Commission was able to bring in 5 of the 9 planetary boundaries. You see them here as climate, air pollutants, nutrients, nitrogen and phosphorus, and then nature, managed and intact nature. Managed nature then being agriculture and forestry, intact nature being the, of course, there are no untouched systems, but the intact ecosystems. And then finally, freshwater, which are represented by both surface water and groundwater, but only here in blue water terms. The breakthrough here in my mind is that the safe boundaries are confirmed, basically aligning with the planetary boundaries, which is what you see in this red-green circle. Green means that justice and safety align. Red means that safety has its own boundary, and the blue are the just boundaries when justice is more stringent, reducing the space even further for safety for humanity. So just to explain this with one example, climate. The safe boundary is assessed today, which I showed you earlier, to be 1.5 degrees Celsius. Go beyond that, and we risk the stability and functioning of the biogeophysical systems on Earth. But the social scientific assessment of maximum tolerable levels of significant harm to people, meaning millions of people affected by life-threatening impacts of climate change, is assessed to be already at 1 degree Celsius. That's the blue line. So justice shrinks the safe and just space, the Earth system boundary for climate, even further. At 1.48 degrees Celsius, we're thereby just touching the safe level, but well beyond the justice level. And this is really important, I think, also to recognize that there is a very high degree of people justice also related to quantifying the space for humanity on Earth. We then tried to take this even further into a governance regime, because if we're talking and recognizing that what regulates the stability of the Earth system, our chances of really holding the Earth system close to Holocene-like conditions is guided by these quantitative boundaries, but inside the boundaries, you have the global commons. You have the large biophysical systems that we all depend upon collectively for the stability of our future. Now, we do have a legal framework called global commons. The global commons are understood since many, many decades as the systems outside of national jurisdictions that are owned by nobody, thereby owned by everybody. And we recognize 4 big global common systems that have legal treaties also: Antarctica, the high seas and the deep seabed, the atmosphere, and outer space. What we have just published a paper coming out of the Earth Commission, which is a paper done together with lawyers, political scientists, earth system scientists, climate scientists, is a proposal to now redefine the global commons in the Anthropocene to say it's not enough to only consider systems outside of national jurisdictions as being global commons, but we also need to recognize a complement, what we define as planetary commons, namely all the biophysical systems on Earth that we collectively depend on, irrespective of whether inside or outside of national jurisdictions, for our life support, irrespective of where we live, meaning all the spheres and basically all the tipping element systems. And here you have the mapping of these roughly 20 proposed planetary common systems. And you see here, of course, all the climate tipping elements are there. So the permafrost, the Amazon rainforest, the Greenland ice sheet, but also the AMOC are systems that we consider today that we all depend upon. And to round this off, we have, because of the urgency of the challenges we're facing, because we are seeing more and more signs of approaching these tipping points that would take these planetary commons to a drift away from resilient, healthy state, we are now going to do a health check of the planet, meaning updating the planetary boundary science and working with Earth observation data providers to quantify at the global level, but also having spatially explicit maps of how we are doing against all the planetary boundaries every year. Because so far, the planetary boundary science has only been able to be updated roughly just like the IPCC every 7th year. Now we'll be able, or we are aiming to do a planetary boundary health check, as we call it, every year. The first one will be launched at the New York Climate Week in 2024, where we do an update of the science with Earth system modeling and tipping point science, together with Earth observations. I'm at a meeting right as we speak with the European Space Agency, with NASA, with Planet.com, with a number of satellite image providers measuring the Earth system to be able to help us to integrate this with the planetary boundary science. This is really exciting, and I look forward also, perhaps several of you in the room are interested in this. I mean, we have so many great scientists at GFZ and AVI at the Telegrafenberg. So, I mean, that's a really important collective community effort, because we are at this critical juncture. We are drifting as a business as usual pathway that takes us very close to dangerous terrain, and we need to rapidly transform to be able to meet this bullseye of a safe landing within safe and just Earth system boundaries or planetary boundaries for humanity's future. And we need to move very fast here. And that is, of course, one reason why we in science also need to start testing new ways of advancing our insights and evidence. So thanks for this. And yeah, back to you.